Hello, welcome to my first video for lesson 2.1, looking at discrete random variables, their probability mass functions, and their cumulative distribution functions. I'm making this video because even though I think that the other video I found on YouTube is a really good introduction to discrete random variables, it does not use some of the notation that we use in the textbook. So I want to just add a little extra video to go over that part. A probability mass function, we use the abbreviation PMF, and it is a function that just assigns a probability, f of x, little f of x, to each value that a discrete random variable takes on. If we have this discrete random variable, x of s, the number of heads in 3 flips of a coin for all the elements of the sample space, we can define it this way. We just count the number of heads. So when we describe the probability mass function, we're going to need to have the probability of each individual value that the random variable can take on. So we can see that these values, our little x's, are going to be 0, 1, 2, and 3. And the PMF is going to assign probability to each of those possible outcomes. Since we have 8 equally likely outcomes here, our probability f of x for 0 is going to be 1 out of 8, because there was only one outcome that resulted in 0. Since we had 3 out of the 8 outcomes that resulted in 1, we're going to have a probability of 3/8 associated with 1. We're going to also have a probability of 3/8 associated with the outcome 2. And 1/8 associated with 3. So if we write out our probability mass function, it should look like this. And remember, our probability that x equals x that's our PMF, f of little x. Now, in addition to writing out all the values of the probability mass function, we can also show the probability mass function graphically in a couple of ways. 2 ways shown in the book are a line graph and a probability histogram. In both of them, the horizontal axis displays the values that x can take on, and the vertical axis displays the PMF, little f of x. The only difference is that in the line graph, it's the height of the line that represents the probability. And in the probability histogram, it's actually the rectangular area that represents the probability. Let's look at some of the properties of a probability mass function. The first one is that the probability mass function f of x is going to be greater than 0 for all of the values of the random variable that are associated with some possible outcome in the sample space. And if we have a value of the random variable that's not associated with an outcome in the sample space, then it's going to have no probability and f of x will be 0. So for this reason, S, our sample space, is called the support of the PMF f of x. Another property is that if we take all of the possible values of x that are associated with the sample space and we add up their probabilities, then they should sum to 1. So the sum of all of our f of x will be 1. And then last, if we have some subset and we're working with a discrete random variable, and we want to know, okay, what's the probability that of that subset? Then we can find that probability by adding up the probabilities of each of the outcomes that make up that event. And that sounds more complicated than it is. Let's take a look at a quick example. Here's the probability mass function that we were just working with. If we are interested in an event A, which is that we have less than 2 heads, we know that the values of x, the number of heads, that's associated with that are 0 and 1. So if we want to find the probability that we have less than 2 heads, we can just add the probability that we have 0 heads and the probability that we have 1 head. So if we add those up, we get the probability of A. Probability of having less than 2 heads is 1/2. Now let's also look at another function associated with the probability distribution of the discrete type, and that is called the cumulative distribution function, CDF. Instead of looking at the probability that our random variable x takes on exactly a particular value x, what the cumulative distribution function does is it tells us the probability that our random variable takes on a value less than or equal to a value little x. We use the notation big F of x instead of our little f of x for the cumulative distribution function. And the cumulative distribution function is actually defined not just for the values that can occur of our random variable, but for all values from -infinity up to infinity. Coming back to our example, we know that there is positive probability associated only with the values 0, 1, 2, and 3, and that everywhere else f of x is 0. So big F of x, or CDF, is going to be 0 for all values until we get to x equals 0. Once we get to 0, we know that the probability that x takes on a value of 0 or less is going to be 1/8. And since the probability of x is 0, between 0 and 1, my CDF is going to take on the same value. (1/8) for all values of x that are greater than or equal to 0, but less than 1, because it's going to increase again at 1. When we get to 1, our cumulative distribution function is going to increase by 3/8. From 1/8 to 4/8. And it's going to maintain that value until it gets up to 2. So f of x, big F of x, is 4/8 for all x that are greater than or equal to 1, but still less than 2. Similarly, at 2, our CDF is going to increase by another 3/8. And it's going to maintain that value until we get to x equals 3. So it's going to be 7/8 for values of x that are greater than or equal to 2, but still less than 3. And finally, when we get to 3, our f of x is going to increase again, this time by 1/8 up to 1, and it's going to stay there because we know that f of x is 0 for everything greater than 3. It's going to stay the same for all values of x that are greater than or equal to 3. So this is our cumulative distribution function associated with this discrete distribution. That brings us to the end of our video.